Welcome to XM, or the course Experimental Mathematics. I'm away on Monday, the first day of classes, so instead I'm going to record the lectures for you to see on YouTube. So let me start by giving you a general introduction to the course. So of course you are wondering, what do we mean by experimental mathematics? And this is definitely one of the main goals of the course, of course, to explain that to you. Maybe the right place to start is to consider the word experiment and compare it with the word as it is understood in natural sciences. So, if you're doing an experiment in physics or biology or whatever, you will usually be perfectly happy to draw a conclusion directly from the result of your experiment. So, if you're Galilei and you're dropping things from the tower in Pisa, and you see that things that are heavier do not fall faster than things that are lighter, then after you've performed this experiment enough times, you will be ready to make a conclusion about the laws of physics. But this kind of thinking doesn't really apply to mathematics and to experimental mathematics in particular. So I'm not going to try to convince you that we can think of mathematics as an empirical science. On the contrary, this main purpose of the course is is to explain that we are going to make experiments that will aid us in the traditional endeavors of mathematics, that is, proving theorems, essentially. So this figure here I'm going to show you many times in the course, and this is essentially the way that I would like you to think of the process of experimental mathematics. So essentially what we will see many times during this course is that we're deciding to look at a certain mathematical concept, maybe some objects, for instance, and then we will create experiments by sort of making a refined hypothesis sequence. So this is what this is supposed to mean. So I have some objects that I'm interested in understanding, and then just from staring at them or guessing, I will come up with some hypothesis saying that these will all have this property or something like that. Then I will make an experiment to see if I can confirm this hypothesis or falsify it. And of course, if my experiment turns out to be successful in the sense that it comes up with a counterexample, then clearly I need to revise my hypothesis. And then the idea is that we sort of keep on going until we break out of this or decide that we don't want to do it anymore. So if we have a hypothesis that can be falsified, then perhaps we're happy to say, now we have a counterexample. This in itself is an interesting result. But maybe we feel compelled to make a more advanced hypothesis which fits what we got out of the first instance of the experiment. Then we can test that experimentally and so on, and we can keep on going. And of course, very often you'll find yourself sort of going indefinitely. So you keep searching and trying to find counterexamples, but there aren't any counterexamples, and maybe that's because you're actually stumbling upon an interesting mathematical result, so something that you could actually end up proving. And the defining feature of a successful mathematical experiment is precisely that it's designed so that it will generate knowledge that will go into the traditional endeavor of proving a theorem. Right? So when you're doing a mathematical experiment, you're not looking directly for an output such as you would do in natural sciences, but you're more indirectly generating information, insight, data that can be used in the traditional approach of making a conjecture, proving a theorem, and so on. And this, of course, is really the fundamental challenge of experimental mathematics, is to design the experiments so that you have the highest possible rate of success. And by rate of success, I mean the rate of success of generating interesting mathematics. And that could be, generating counterexample that shows that certain things are more complicated than you might think. It could be generating a hint for a proof, or it could be generating maybe just a conjecture or the general idea that something is interesting to look more closely at. So here's my definition of experimental mathematics. So the systematic investigation of concrete examples of a mathematical structure in the search for conjectures about its properties. And then in parentheses I'm putting using computers. Because of course in a course like this one, and certainly in this day and age, computers are extremely important tools for doing experimental mathematics. But in a moment I'm going to show you examples that are much more traditional and predate computers by several hundred years. So I want to emphasize that the idea of experimental mathematics is certainly not new, and you might even say that there was a time in the history of mathematics where almost all new mathematics was experimental in nature. So what's important to focus on here is that the output of a mathematical experiment is not just in itself is usually not a yes or a no or an answer to an important question. It will be something which is a little less directly useful. So at the top of usability would be a counterexample, right? So if somebody says, has been saying this is a true statement, and by using an experiment, using a computer, we can find a counterexample. This, of course, is a mathematical end result in itself. So this is something that you might decide on down the road to put in a mathematical textbook or in publish in a paper or whatever. So this, of course, is a completely standard way of producing mathematical content. And this is also something that traditionally would not be a problem to publish. You could write a paper, submit it to a journal to say that now I found a counterexample to this problem that some other people perhaps have found interesting and made conjectures about. But very often when you're doing an experiment, you will have to make do with less directly useful things. But so one thing which is also extremely useful actually is a reference to the mathematical literature. So I'm going to show you in a couple of weeks when we talk about symbolic inversion, which is one of the main tools of experimental math. I'm going to show you examples where mathematical experiments really, the main use of them is to establish a connection to the literature. And this is something which is perhaps a little bit surprising because, of course, we have a huge amount of mathematical literature, but we also have very useful search engines, and there's MathSciNet, which is a complete index of essentially all papers published within the last 100 years or something like that. So you might wonder why it's necessary, but actually very often it's difficult to find interesting or useful literature where you're studying something. And this, of course, is particularly the case if I'm studying a math problem over here, and it turns out that I actually need to use some math that's been developed over here. Then I have to establish a connection. And how would you go about doing this? That is actually not so easy to obtain using, for instance, Google. So what very often works is that you can make an experiment. For instance, you can try to count objects or something like that, and then you will have a sequence of numbers. And a sequence of numbers is a much more predictable way of searching in the literature. And sometimes you will simply be able to say, well, this sequence of numbers, it comes up over here and it comes up over here. There has to be some connection. And when you study that, you will then be led to a proof of a certain interesting mathematical statement. So this is also an output from an experimental investigation, which can be very useful. But much more often, it will be a little bit more nebulous what you get out of a mathematical experiment. So I'm putting it down as a hint. So if I've studied something and there seems to be some pattern in the output of my experiment, this pattern could somehow inspire me to look for a proof that uses this common property. If there's a certain constant that comes up, maybe, I don't know, square root of pi, that will say, well, square root of pi, that seems to come up in a normal distribution, so perhaps that has something to do with that. So this is all very vague, and that's why I'm calling it a hint. But this, of course, is still quite useful because it can give you information in the production of the standard, the traditional output of a mathematical process, which is a theorem and its proof. But further down the line, it could also simply be a conjecture. So it could simply be that I've made an experiment that makes me think that it is probable that a certain mathematical statement is true. And this, in fact, is probably the way that most mathematical theorems come about, maybe not by computer investigation, but then perhaps by case-by-case investigation, that mathematicians will look at structures more or less systematically, more or less computer-based, and they will decide, well, it looks like this might be true. And this, of course, is the first step in establishing that something is true, is that you get the idea that it could possibly be true. And in fact, very often, that's what you get out of an experimental approach. The experiments will not, you cannot be certain that the experiments will help you prove that something is true, but at least they can give you the idea that it is true.